Mr. Chairman, ladies and gentlemen, first of all, thank you for having me in Belgrade. As the Chairman said, my company is Cool Space. It's a United States manufacturer, although, as you can probably tell by my accent, I'm not from the United States, I'm from England. But don't worry, I'm not going to talk about Brexit. Okay, so this presentation is in basically 3 parts, and I created this presentation because in being involved in the evaporative cooling market for many years, I find there's almost a misunderstanding about it. People get a little bit confused between air conditioning, evaporative cooling, so this is a fairly simple and straightforward presentation about what evaporative or adiabatic cooling is. What is it in practice? How do we actually then kind of apply it? And the whole emphasis of this presentation is talking about very large buildings, and I'm mainly going to be talking about factory spaces, which is conventionally very, very hard and expensive to cool with a conventional direct expansion air conditioning system. I'm going to then touch on a little bit about designing a system and then finally look at some of the applications. Now, here we go. So, what is adiabatic cooling? What is evaporative cooling? And for this, I'd like you all to close your eyes and remember the last time that you were by the seaside on a lovely beach holiday. And centigrade. But when you get on the sea, when you go on your boat or you stand by the ocean, it's 22 degrees. So what is happening to you and your body? Well, in simple terms, what is happening is evaporation of water being drawn into the airstream, the movement of air across the sea or a lake or wherever you are, and in that process it displaces heat. Simple as that. Here we have a graphic which shows what the science is behind it. This is a psychrometric chart. I'm sure you are very familiar with this, and along the bottom axis you will see the dry bulb temperature, and on the curved axis to the left you will see the wet bulb temperature. So I've taken this as an example in Athens in Greece, where I was in the summer having a lovely time, and what actually happens is as you're humidifying the air, what we're doing is suppressing the dry bulb temperature by the use of humidity. So at a 90% relative humidity there, you can see that the resultant temperature effect is 22 degrees. You can see that at the bottom of the graph there. So that is actually what's happening, and this is a psychrometric chart. Wherever you are in the world, you can actually figure out actually what the resultant temperature is going to be from that suppression. So that's the physics. How do we apply it? I'm here to talk about evaporative cooling in general. There are 2 types. This is, I'm showing on the graph there, a portable evaporative cooler. So the way we actually replicate this, on the right of the graphic there you will see a cellulose pad. This is a cross corrugated cellulose pad. We draw the hot air in through the device by the use of a fan. Okay. We then use a water system to sprinkle the water into that pad and then draw the air through, just as we saw on the graphic by the seaside. Works in exactly the same way. And as it is discharged, the evaporation has created this effect of displacing the heat. So immediately outside of the cooler you feel directly very cool. Very importantly, because people get a little confused between the difference between a misting cooler and an evaporative cooler. A misting cooler actually uses direct condensation onto a body to create an evaporation effect off the body. This is a different system. The discharge from an evaporative cooler should be a mistless discharge. There should be no water actually coming out in condensation form. It should be suspended in the air stream. So what would be the cooling effect in Belgrade? I've taken the same psychrometric chart here, and you can see here that peaks of average temperatures just under 34 degrees. Using the pad that we have, it's a Munters pad, we probably get an efficiency of 85%. It's not feasible to create 100% effectiveness of these devices. So the resultant temperature by using a device such as this would be a 23 degrees outlet temperature. So that's a 10 degree delta T drop. Now, because not everybody is armed with the psychometric chart, what we tend to do is just put it into a nice summarised format. So if you know the dry bulb temperature, if you know your relative humidity in an area, this chart will actually give you a very clear guideline of actually what you would expect the temperature drop to be from the cooler. The second point is that, as we know, ventilation and air movement and air speed does actually create an additional cooling effect. So generally with an evaporative cooler such as ours, you will get an additional 2 or 3% cooling on top of the, in addition to, shall I say, the temperature drop. The second thing people ask me, well, okay, that's great, Simon, thanks very much for that, but how much water does this unit consume? Again, we refer back to our psychometric chart. Along the right-hand axis there, you can see the grams per kilogram of moisture content and the difference between the two. So, for instance, again, in peak temperatures in Belgrade, for instance, a unit which is just, moving about 16,500 cubic meters of air, you would be on full speed evaporating water at a rate of 89 litres per hour. So that's the amount of water it uses, and obviously depending if you've got an appliance which is actually delivering more airflow, therefore the higher evaporation rate. This is why most evaporative coolers are controlled on a fan inverter, so you can actually turn down the airspeed and air volume. Therefore, the cooling effect is pretty similar, but obviously your evaporation rate will then drop. Okay. So that's the basic thing about, well, okay, that's the cooling impact. Well, how about the environmental impact? And I'm mainly thinking about this, again, in terms of how we are cooling very large spaces. Think of a factory. In terms of their electrical usage, an evaporative cooler such as ours uses very low electricity, less than 6 amps draw, less than 4 watts. Probably the use of one of the coolers would end up about 530 kilowatt hours per year. It's very low in energy use. People ask me quite often, okay, how does that compare in terms of kilowatts against an air conditioning unit, DX, for instance. And generally with evaporative cooling, we don't measure it in kilowatts, but you can do the calculation which is there. So again, for a 16,500 cubic meter per hour appliance, delivering a 10 degree delta T, you're probably looking at about 55 kilowatts of cooling performance if you were going to make the comparison with a traditional air conditioning unit. And my point is, if you've got very large spaces to cool, how much would it cost to run a 55 kilowatt DX aircon system compared to the evaporative cooler? And the answer is it would probably cost you 10 times the amount to run the air conditioning unit. And in large spaces, a lot of the time, it's just not practicable in terms of the capital cost of doing so. What's the ergonomic impact? I saw a very good presentation earlier from one of the delegates here about the effective temperature on people. This is a far more simplistic graphic. It's a piece of NASA research from the United States, and it states clearly that for every 1 degree Celsius above 25 degrees Celsius, human productivity will drop by 2%. So again, in a factory working environment, if you're at 40 degrees C, it's generally, the workforce is probably 30% less effective or productive than they would be at 26 degrees C. So quickly, we're going to look at designing a system. The most important aspect about any evaporative cooling system is because we are creating humidity, therefore ventilation requirements are paramount in our mind when we're designing the system. So with that, you will know all this, but the 3 forms of ventilation within a building, there's natural, through open windows and doors, creating stack effect or cross draft effect, and then we can have mechanical extraction or input, and we can have a combination of both. We mentioned earlier again in some of the previous speakers about air changes per hour, and generally these are rule of thumb, I call them guides, that if a building is very tightly well made, sealed, you're probably only going to get half an air change an hour naturally. Oh, and if you have a building that's pretty loose or old, or you've got the windows and doors open a lot, you've probably got between, well, at least 2 air changes an hour, sometimes 3, depending on the outside conditions obviously as well. And obviously any mechanical ventilation has got to be dictated by the fan performance in terms of the air movement of it. Okay, we're not going to go through all these. These are, we use in the UK, the SMEITS recommendations, and you can see at the bottom there, factories and workshops recommend an air change rate of 8 to 10 to create a comfortable environment on ventilation. That's from the SMEITS Guide 2011, reference 671552, which you can see there. Okay, so let's look at 2 scenarios. One is a full coverage scenario. I've got the whole of the space, it's enormous space, and I want to actually look at cooling the whole of the space. So, okay, the simple way of doing it is to take the complete volume of the building, we multiply that by the recommended air change rate. I've taken a recommended air change rate here of 8 times. So if we've got a building 100 metres by 37 metres high, the ventilation requirement in that building will need to be about 168,000 cubic metres. We then take our appliance, whatever the cooler may be, and we say, okay, we divide the cubic capacity of that appliance into the ventilation requirements. So in this case, you'd end up, you say, I would need 9 evaporative coolers. And if you were looking at a whole a whole coverage project, you would probably consider looking at an evaporative cooler that goes through the roof, such as the graphic you see there, that can then be distributed into the space by the use of a plenum duct or a longer ductwork according to where you want the cooled air delivered. Okay, but in reality, full coverage, especially in a factory, is not always required. In fact, sometimes you just want spot cooling. You want people who are buying machinery to be cooled. The other things to consider, if you're going to put a lot of coolers through the roof or through the walls, sometimes that's prohibitive, especially on a retrofit project where you may have a lot of things internally in the space that prevents you doing that. So in this case, we can use the portable cooler. And again, because we've got some experience of this, we would say we can actually give a rule of thumb guide by area. So if you've got an area of 600 square meters that you want to cool as a spot, then you would probably be needing a device that moves about 45,000 cubic meters of air, subject to the fact that obviously there's a competent performance within the unit to deliver the cooling in terms of actually how I described earlier how the actual cooling works. And you can see there, depending on the size of the cooler, will depend on the area that it's going to actually cool. Other key considerations are you can say, well, I'm going to still check the ventilation rate in this area. So it's really important for portable coolers that you keep, unlike the air conditioning thinking, here we need to keep all the windows and doors open. We need to make sure there's adequate ventilation. If we do that, we can assume there's a natural ventilation rate within that building of 2 air changes. So again, I take a lot of my time telling people, keep the doors open, keep the windows open. Very important to not over-humidify the space. If you were looking at an area of, say, 1,500 metres of a building that's a lot larger, you could still apply the theory that I said before. You could say, well, I need 8 air changes in that particular area, which would be 84,000 cubic metres of ventilation. Time. Okay, right. So anyway, I'm just going to fast forward. I've got 2 minutes. 2 minutes. Okay. So think ventilation. Think also free blowing, because there's no point of putting evaporative coolers into a space where there's obstructions. And I'm just going to whiz through pictorially some of the places, large spaces, that are perfect. And of course in outdoor situations as well, they're very effective. Sports areas are great as long as you've got the ventilation requirements right. Okay, there are certain areas where evaporation coolers can't be used, certainly where you have closed spaces. There is, I'm going to rush through this, there's very little risk from the Legionella, and there's an ASHRAE document that I can refer any delegate to point you in the right direction on that, but the risk of Legionella is negligible to zero. And on that basis, I'm sorry that I've overrun this, Mr. Chairman. I would be happy to take any questions.
Okay, floor is open for the question. First question I have, how you prepare the water?
How do I prepare the water?
Quality of water.
Well, we use these appliances all over the world, and it's true to say that the quality of the water varies considerably. There are little devices that you can buy, proprietary devices into the water line that electrolytically stimulate the water and soften the water. We also can have devices that you can put into the reservoir to soften the water. But I would be practical and say you need to understand the hardness of your water in terms of the calcium content prior to doing the design, and then you've got to be quite rigorous on the maintenance of the unit. The maintenance is straightforward, but you need to be able to clean the pads easily. So yeah, it is a key factor.
How you control the humidity? Because large humidity is not for the comfort. Okay, we know this system for the cooling for many years, and it is nice for the dry environment, for the hot, humid environment, yes, like California or Florida.
Well, we do sell them into Florida for sure, but obviously the cooling effect is a lot less. You're correct, and you're probably only talking about 4 or 5 degree cooling effect as opposed to here a 10 degree cooling effect. For a fixed cooling system, you can use a humidistat to control the coolers to turn them off when they've reached the requisite humidity. As far as the portable ones are concerned, generally we're putting them into a space where there's relatively a big volume turnover of air within a space, and we're putting quite a small amount of humidity in, so it tends to dissipate that problem. But you really wouldn't, as one of the earlier speakers said, you certainly wouldn't want to be going over 60% relative humidity even in the factory. So a lot of it is to do with positioning, as I said earlier, in factory spaces by practically putting them by windows and doors. But for a portable device, there's no other way of controlling it.
Okay. Some other questions? No?
Thank you for your time.
Thank you.